Hello, welcome to my presentation. Today I'm going to talk about the field level greenhouse gas emission estimation of thermal enhanced oil recovery method. Well, firstly, I'm going to talk about the project's motivation and introduction. So the motivation starts from the question that how much more oil do we need by the end of this century? So here comes to the answer. Our group has collected all the projections from all the available resources, companies, the government or non-governmental organizations, even including the notoriously rigorous regulation, the Intergovernmental Panel 2016. This is a cumulative oil consumption in the next few decades. Almost all credible scenarios show decades of oil demand. The IPCC low emission scenario gives about 1 trillion barrels of oil consumption by the end of this century. This is equivalent to all the global conventional reserve. If we assume the recovery factor is about 30%, then only 0.3 trillion barrels of oil can be produced. Then the next question is where to find that 0.7 trillion barrels of oil. Apparently, heavy oil is a good option. This map shows that heavy oil reserve distributed to almost all the continents except the poles. California, Venezuela, and Russia all have over a trillion barrels of reserve. So let's take a closer look at the reserve in each region. The North and South America accounts for 70% of global heavy oil reserve, and surprisingly, the Middle East has over 1 trillion barrels. So the total OIP of the heavy oil and bitumen is about 8.8 trillion barrels. About 90% barrels are recoverable by thermal enhanced oil recovery method. If we consider the lowest 40% thermal recovery, that's about 3 trillion barrels is productable. So, however, we got bad news for heavy oil. This is the research from our group. We run over 9,000 oil fields in the world, and we found that upstream account for more than 20% well-to-well life cycle greenhouse gas emissions. For the highest carbon intensity quintile, about 41% of crude volume comes from high flaring fields, while 18% comes from heavy oil fields because of thermal enhanced oil recovery method. Over 70% upstream emission comes from steam generation by burning fuels on the surface. This work only showed that heavy crude upstream operation could generate large emissions, but my goal is to figure out how exactly emission changes with different injection and production profile within one specific field. The tool we use to estimate the emission is called MITAB20-24, which is short for the Oil Production Greenhouse Gas Emission Estimator. It's an engineering-based life cycle assessment tool that estimates the greenhouse gas emission from the production, processing, and transport of crude petroleum. So it only covers the well to refinery emission. The input includes oil production volume, number of producing and injecting wells, reservoir pressure and temperature, well to oil ratio, steam to oil ratio, etc., etc. And all the input are in the field level. My research lies in here, which is to generate field level rate history match and forecast, and then use MITAB to have a dynamic emission evaluation. I will cover it more in detail in the next few slides. So the method I'm using to generate field level forecast is called pattern-based modeling. The pattern-based modeling is a semi-conceptual analytical model that generates a field level production forecast using patterns. A pattern is a flow regime with special arrangement of producers and injectors. This shows the classic invert 5-spot pattern with steam flood. In the thermal enhanced oil recovery field development, the steam is usually injected into patterns in sequence. It gave me the insight to use pattern as the fundamental building blocks. If single pattern has been well studied, the field level rate can be easily estimated by making assumption that the summation of the performance in each individual pattern is equivalent to the field level performance. So in the single pattern, we found that steam always goes to the impermeable overburden immediately due to the vast density difference between heavy oil and steam. Once the steam reaches the bottom of the producer, the oil reaches its peak rate. At the same time, the steam chest is formed. The steam chamber, which contains saturated steam, pushes the oil below using the latent heat, and oil rate falls into a hyperbolic decline. I'd like to show you how steam moves in the cold oil reservoir. This is a cross-section of 5-acre 5-spot reservoir. The injector is perforated in half. The light color shows the high saturation of the steam. Even though steam is injected in the lower layer, it moves to the top immediately after the injection. And when it reaches the top layer, it starts to form a chamber and drive the oil below it. Then we split the steam drive into two mechanisms: frontal displacement before steam breakthrough and gravity drainage after steam breakthrough. Before steam breakthrough, we also consider the condensing water rate using critical time. So we could build a correlation between steam movement and oil rate. The cumulative oil rate can be written using this function. The Vs is the steam volume. Basically, all the question build the type curve shown on the left. The oil rate changes with the steam rate. The type curve is flexible to all range of injection rate. This plot shows three cases. It also shows that the larger injection rate would result in faster steam breakthrough and larger oil decline. The single pattern type curve analysis is also validated using simulator. Here I want to mention that the water rate is also derived from oil rate by using multi-temperature fraction of flow. The dashed line is the analytical result and the solid line is the simulation result. We could see that both water and oil rate have a good match. We also run another case by adding multiple patterns in the same acreage. It shows that for multiple patterns with similar reservoir properties, the oil and water rate could be forecasted using one large pattern. It follows the superposition principle, which is very useful for the upscaling. Okay, I would like to show the pattern-based modeling using two cases. One is the Kern River field, which has over 50 years steam flood history. Firstly, this is the steam injection rate plot. The triangle symbol indicates the historical injection. The dashed line shows the history management forecast injection rate using pattern-based modern method. The stacked plot shows the matched rate for each pattern. Based on the type curve analysis, each pattern has the oil rate type curve. Then the overall field level oil rate is shown here, and the water rate is shown here. As comparison, we also plot the steam oil ratio and water oil ratio. We can see that Kern River has a 15 years high steam injection rate between 1975 to 1990. This is due to the 1970s energy crisis. The oil price increased more than 50% during that period. The operators believe that more steam injection will result in more oil. This is not the case for steam flood. So the oil rate increased just slightly, but steam oil ratio doubled. Then the people realized this problem and until now keep the steam oil ratio in the range between 3 and 4. The next step, we put the result into greenhouse gas emission estimator. The red line is upstream life cycle emissions. The orange line is the carbon intensity of the steam generator, and the green line is the life cycle emission converted to 1,000 tons. As I mentioned, this 15 years over injection almost doubled the overall CI, and this is all only from steam generation. The carbon intensity range for Kern River steam project is large, which is about 9 to 43, while the average CI is 24, and the unit is in gram CO2 equivalent per megajoule. The model shows that in 70 years, the upstream generates about 3.5 million tons CO2 equivalent, and the average emission is about 380 tons per day. From the sector emission chart, it shows that about 91% of emission comes from steam generator alone. We also ran a new steam flood case. The oil field is Mukhaizna in Oman. The field started to do steam flood in 2005. The challenging part for this new steam flood field is that we could only get access to limited data from the public sources. The rate we have is designed steam injection rate from field development in 2005, and we know that the steam flood pattern is horizontal well pattern. We run the pattern-based analysis based on that information and have this result. Similar to Kern River plot, the triangle symbol is the design steam rate and the dashed line is the forecast. The steam rate for each pattern is shown in the stacked plot. We have the oil rate and water rate forecast in the green line and the blue line individually. The steam-oil ratio is low in this case due to the horizontal well pattern. The results show a sudden increase of steam-oil ratio after 25 years of injection due to a sudden drop of oil rate, but the average steam-oil ratio is still low. So let's see the emission in this case. The carbon intensity range is narrow, which is from 6 to 16, and the average CI is about 11 grams CO2 equivalent per megajoule. The 30 years upstream emission generated about 0.3 million tons of CO2 equivalent, and the average emission is about 28 tons per day. Horizontal well pattern increased the contact area steam to oil and reduced the amount of steam injection. So from the sector analysis, in this case, only 73% emission from steam generator. Well, to the summary. All credible scenarios show decades of oil demand remaining, at least 1 trillion barrels of oil needed by the end of this century. But the productive conventional oil can only supply 30% of demand. Global productive heavy crude is over 3 trillion barrels. 90% of heavy oil could be produced using steam. Heavy oil field accounts for over 20% of high CI field due to the steam generation. A detailed emission analysis using GHG is necessary. Pattern-based modeling is introduced to generate field level rates forecast for steam flood. Oil rate is generated using type curve analysis, while water rate is generated using multi-temperature fractional flow. Both methods are validated by simulations. So we have two case studies, Kern River inverted 5-spot pattern, large data sets, versus Mukhaizna horizontal pattern, limited data sets. Two case studies demonstrate that the power of using PBM to have detailed field level emission profile. We would also like to thank you the funding support from these organizations, and thank you to listen to my presentation.